Hi, and welcome to Allen High School's discussion of bonding chemistry at the pre-AP or honors 10th grade level. Now, we were talking about Lewis dot structures, and we saw this, some of you already noted this. There are times when there's a double bond, and it's typically going to be a double bond to an oxygen, and it really could be one of three places, depending upon where you started filling out your octets. Now, these are called resonance structures. To resonate means to match energy. So these are equal energy. And I know these arrows are written as if it flip-flops back and forth from one to the other, but it doesn't. None of these is really a true representation. We will draw them as part of our, if I asked you to show all of the possible resonance structures, because by drawing these possibilities, they lead to the actuality. And so when I was crossing those out, I was just being I was exaggerating just a little bit. I just don't want you to think it flip-flops amongst these three. So we have these three possibilities, and notice that there are 4 bonds, 1, 2, 3, 4, shared amongst 3 peripheral atoms, the 3 oxygens, 1, 2, 3. And if it's spread out evenly, we would get 1 1/3 bond each. And that's what scientists find when they break these bonds. So those dotted lines represent that the electrons that we're trying to show here in these double bonds, so those electrons there and these electrons as we're trying to show those different shapes, okay, they're not really double bond. Instead, those 2 electrons have freedom of motion amongst the 3 possible bonding regions. And so we use dotted lines to indicate that it's not a full bond. And in fact, it's much closer to 1 1/3 bond each. So that's, called resonance. Now, we saw that with the nitrate ion as well. So if we draw the nitrate ion, we have the 3 oxygens. We have 5 valence electrons from the nitrogen. I've got 3 oxygens, each bringing 6. And don't forget that little extra charge. That extra charge means there's an extra electron. So I have 24 electrons to play with here. So remember, we make our bonds. Some of you are trying to do shortcuts in class today, and there's no shortcuts. Follow the guidelines. Make your bonds. I like to satisfy my central, and then let's do peripherals. That's 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, this is when we would have said, okay, the left oxygen is deficient, so we're going to share some more. So we would put our double bond there. But in reality, and I'm just going to sketch out the structure to save time, there's no reason why that double bond couldn't have been here. Depends on how we started to distribute. Sorry, let's not forget our brackets and charges. I'm afraid if I go any further, I'm going to forget that. So the double bond could have been on the bottom one. Now, you'll need to fill in electrons. I'm just sketching it out to make a point. Or it could have been on the right one. Okay, I don't want to just waste our time doing dot after dot after dot, okay? So the key is it's not any one of these. None of these provide an accurate representation of reality. So we have equal energy possibility, and the true is in between. So what we do is we'd take that double bond and we'd put dotted lines. Sorry, Mimio's being a little jumpy today. Sometimes it does that. Put dotted lines to indicate it's spread out, and then brackets and charge. Okay, so now let's take a look at these and see which ones have resonance. This has a double bond, but there's no place else that double bond can be. Hydrogens can only have a single bond. So this is a no, all right? We have to be able to move it in an equally possible location. Now, sulfur trioxide has a double bond here, but there's no reason why it couldn't have been on that oxygen or that oxygen. And the reality is a hybrid of those. So yes, that would exist as a resonance structure where we'd have the sulfur to the 3 oxygens, and that extra bonding density would be spread out like that, okay? This has a triple bond, but there's no place else that triple bond can be. There's not an equal energy possibility, so that's a no. Well, this has a double bond, and this has a double bond. No place else to put double bonds. You can't move that double bond to an equal energy possibility, so that's a no. Okay, we will do London dispersion, Lewis dot structures for polyatomic ionics next time. So until then, this is signing off.